So hello everyone, this is the third lecture in the series of lectures of fundamentals of physics, and today we will start with a new chapter, and that is called units and dimensions. It's a very fundamental chapter in your course, and we will discuss it today. So one of the first questions that comes up when we talk about units and dimensions is, why is measurement necessary? So to determine the magnitude of a physical quantity, you need to measure it. So there are many ways to measure that thing, and fundamentally the heart of it lies in understanding what units do you assign it so that it really makes sense in the system that you are working with. Now, the title of this topic is Units and Dimensions, but as most of you might realize that there is a difference between these two, though both are used almost interchangeably, but it's not the thing. There is a fundamental difference between the two. So the difference between units and dimension is that a dimension is a measure of the physical variable, while a unit is a way to assign a number or a measure to that dimension. So for example, length is a dimension, but it is measured in units of feet or meters. So that is the fundamental difference between these two. And as we move ahead, we see the necessity of measurement in our daily lives as we compare to similar physical quantities, as in point number 2, and to prove physical laws or equations. So at the heart of proving physical laws and equations lies homogeneity or units, or the way we sort of analyze units and dimensions, right? So physical quantity in general is defined by magnitude, which gives a numerical value to it, and a unit, which gives the base value. So for magnitude, we say how much of that quantity is present within our calculation, and the unit gives what value should we assign to it. Is it in meters? Is it time? Is it weight? Or is it something else? Is it current? It can be anything. So unit takes care of that, while magnitude gives how much of that fundamental quantity is in the system at present. Few points to consider when we are talking about units are that for units, the ratio is a numerical value. It does not have any units, and it can only be used to compare similar quantities only. So for example, if I take a ratio of torque to work, I get sort of an expression of Newton meter by joules, though it is ideally, if we consider a dimensional analysis of this thing, you will see that it should be unitless, but then the way it is written is different. So fundamentally they are not the same. Newton meter and joules are not the same way to compare torque and work. So physically they are different. Okay. And then we have scalars, which are defined by magnitude only, as we have dealt with in chapter 1, and that follows basic laws of arithmetic, and vectors that has magnitude plus direction. But above all of that, it is noteworthy to say that the units also follow along with scalars. So if I add 10 liters of water with 10 liters of water, I can add it nicely, but I cannot add 10 liters of water with 10 degrees centigrade. So that is not allowed, right? So this is the artifact of units, that it follows the law of homogeneity, and that is at the heart of dealing with units and dimensions. So when we talk about units, the basic fact lies in understanding a fundamental and derived units. And as the name suggests, fundamental units are the building blocks of all physical quantities if they are defined in terms of the units. So some points to consider are the base quantities are also known as fundamental quantities, and they are independent of each other. So as you might remember, in chapter 1 we talked about the orthogonal coordinate system, and in orthogonal coordinate system the axes are independent of each other. For example, x-axis, y-axis, and z-axis are independent of each other, and they are known as the primary coordinates, right? So the primary axis, right? So this is also known as the base quantity. So you can imagine it like that. One fundamental quantity does not depend on the other, and that is the reason why they are fundamental, right? They are the building blocks. They're also known as absolute quantities, and this statement defines the completeness of your physical quantity, because they shape all physical quantities in different proportions, right? And then you have all other physical quantities are derived from this, as I stated in point 2. That's basically a reiteration. Point number 4 states that what exactly are these physical quantities? What are we talking about? And for our case, it is mass, length, and time. So these three are the building blocks of all physical quantities, and that is also known as base, absolute, or fundamental units. So from this discussion, we see that basically there are three fundamental quantities, and these three fundamental quantities are used later in this particular lecture to show that they form what is known as derived units, as you see in the next section. And derived units, as the name suggests, are physical quantities which are derived by suitable, and this is important, multiplication and division of different powers of the base quantities or units. So since I have already said that these are base quantities and units, they are the building blocks, but one more thing which is noteworthy to consider is they are formed by suitable multiplication, division of different powers of the base quantities. We'll get back to this artifact of derived unit shortly, but it is good to note that it's only the multiplication and division that really affects, and different powers of it. So different exponents of the fundamental unit really yields several physical quantities that we will talk about. Since we are talking about the fundamental units, what are the system, what are the combinations that have been used throughout ages? So the first of them is the Gaussian system, also known as the CGS, as all of you might know, where mass is expressed in grams, length in centimeter, and t is time, and that is in seconds. The other is the MK system, or the Georgi system, and that is the most prevalent one that you might have been seeing from childhood. That is, mass is represented as kilograms, length is in meters, and time is in seconds as usual. There is no variant of time in either system. And then the American system uses the foot-pound measure, where mass is in pounds, length is in foot, t is in time. And this is pretty much the three major systems by which people have used and calculated other things. There is another unit called the British Trade Unit, BTU, but sort of no one uses it pretty much now. People usually use the SI system, which is much similar to the MK system at this point. So apart from the three big systems that we have seen so far, there is something which is known as the practical units, which does not fall under the fundamental units, because these are units that we use in our daily life, and they have implications because we do not express these quantities as fundamental quantities. These are not fundamental. However, we use them so much that they have become a normal terminology. For example, if you have all of you have heard about milestones, right? So this word mile is basically 1.63 kilometers, but we never say 1.63 kilometers stone, right? We say a milestone. So that's the terminology that we use, though it is not a part of any system. However, it is used in our jargons. And then 1 ton is equal to 1000 kilograms. So in an environment where you have ton as the unit of consideration, you do not usually express them in terms of kg before you consider it so far. And same is the case with pounds and kilograms. And then we talk about how do you get a physical estimate of the standards of length, mass, and time. So one might ask, how did they first come up with how much is one length, how much is 1 unit of length, how much is 1 unit of time, etc. So I'll just go through a brief experimental artifact of how length, mass, and time are sort of given a metric. So meter is the distance containing 165.0763.73 wavelength in vacuum of the radiation corresponding to the orange light, red light emitted by an atom of krypton-86. This is simply a work of experiment, and that's how they have come up with a distance for meter, and it's fairly accurate. The accuracy is what matters in all these experiments. And mass of a cylinder, mass, that unit is, so mass of a cylinder made of platinum iridium alloy, that's basically the 1 kilogram. That's how that's 1 kg, and that is kept in the International Bureau of Standards somewhere in France, but I'm not sure about this fact. So yeah, so this is basically, they have kept it as a standard, right? Time, on the other hand, is defined as the time interval of 9192631770. You really don't have to remember this number. I'm just giving an estimate of how these experiments have been performed in order to ensure that the fundamental quantities are extremely accurate up to the point that humans don't have any issue when they are doing problems or they are doing things in their day-to-day lives. So they can take that as the absolute unit. That's the reason why fundamental units are called absolute units, because they are perfect. So all other quantities are measured with respect to this quantity. That's why they're also, their experiment, the way they are found out, the way they are evaluated, calculated, must be accurate, right? So as we talk about units, we realize that at the heart of units is dimensions, because dimension is the way by which you can really measure, give a metric to understand, quantify how much, what are the composition, what is basically the composition of your derived quantities, because it is formed from a combination of base quantities, right? So going word by word, dimension is product of the powers of the fundamental quantities, right? It's as simple as it can go, because for this case we have already said that it mainly depends on the product of the unit, the fundamental units that we have talked about previously, and the exponents that each fundamental unit has, and the product of them, and that will give rise to a physical quantity. So for example, we consider force, and that is essentially mass into velocity by time, that is mass into acceleration, and that can be written as mass into length divided by time square. So our final result, that is the fundamental unit form, is given as m has one exponent, L raised to the power 1, and T raised to the power minus 2. So the dimensional equation is written as in this form, and we will follow this rule all throughout the discussion. Keeping this in view, we see that a number of physical quantities have same dimensional equation, and that really makes it confusing at some point, because it is very difficult to distinguish between two physical quantities if you have the same dimensional equation. In that case, you need to go through the problem to decide and get some confidence in what physical quantity, in what physical domain your physical quantity is. So the quantities having the same dimensions, frequency, angular frequency, and angular velocity. So these quantities have the unit, which is second inverse, and then you have work, internal energy, and torque, that has units as you see over here in point number 2, in which 1 is an exponent of m, t, L to raised to the power 1, and t, which has an exponent of minus 2, all have the same units. But just seeing the dimension, seeing the dimensional form, it is very hard to visualize what exactly we are talking about unless the problem stated is given. And then you have a momentum and impulse, they both have the same units, though physically they are not very same. Their units are the same, but when you deal with Newton's laws of motion and then go into the preceding sections, you'll see that they have some relation between them, and most importantly, the dimensional form is the same. So now coming to the most important part of today's topic is the application of dimensional analysis, and the first point that we will focus on today is finding the unit, and that's where the importance of the dimensional analysis comes in, that it can be used to find the unit of a physical quantity in a given system of units. For example, when we say that I'm finding the unit of a physical quantity, it means that, let's say if I have work, and work is basically force into displacement, as you know, and force is a unit of the dimension of force is mass into length into t to the power minus 2 multiplied with length, which is the distance, sort of you can write it like that, and then you have the final form, which is this one, ml square t to the power minus 2, and then it can be expressed in mks on then and or also in cgs, right? But you need to arrive at this expression. So using basic quantities, you can arrive at a unit of other physical quantities. That's the basic thing that you can do with dimensional analysis. The second point is you can find dimensions of physical constant or coefficients. It means that, let's say if you are given a relation, then you can find out what is the dimension of the constant that is given in the equation. So we follow two steps. First, write the equation, get some confidence that your equation can be used to figure out the dimensional form of your unknown constant, and then balance the coefficients of both sides. And we'll see later that we have used this property of homogeneity on both sides to figure out a lot of things, including dimensional similarity, right? So force is given by this expression, and the gravitational constant, as you can see, this is the equation, so the expression of force that relates the two masses and the gravitational force between them, separated by distance r. And from the expression we see that g has this value, and we replace all these values with their dimensional form corresponding, and then we arrive at the dimensional form. So we see that using dimensional analysis we can find the dimensional form of a particular gravitational of particular constant, and for this case we have the gravitational constant, right? So these are two points that we discussed. And moving on to third, we see that it can also be used to convert a physical quantity from one system of measurement to the other, for example from the MKS to the CGS, right? So for example, if we consider a very classic example of converting newtons to dynes, in that case it has 1 Newton is equal to mass length t to the power minus 2, which means it is an MKS already, which translates to kg meter per second square. But then we know that kg is equal to 1000 grams and then 10 square centimeter into second inverse square, and then you have 10 to the power 5 gram centimeter per second square. But we know that 1 gram per centimeter square is 1 dyne. So now we say that 1 Newton is equal to 10 to the power 5 dynes. So we can establish relations between corresponding physical quantities in one system with that of the other system easily using the dimensional analysis, right? So these 3 points were very fundamental, because in most problems you might need to convert, you might need to find out an unknown, you might need to get dimensions of physical quantities from this expression. But the fourth one is very important when you're solving numericals, because it might so happen that you're given a problem and you're asked to verify whether the equation is correct or not. In that case, the first thing that should come into your mind is whether I should check if the dimensions of the right hand side are the same as that of the left hand side, right? And the principle of homogeneity is exactly the same. The dimensional form of the right hand side should be the same as the dimensional form of the left hand side of the equation that is given. So the dimensions of each term on both sides of equation must be the same, and that is very fundamental in all of units and dimensions. It should be the same, otherwise there is no point in establishing a relation or an equation in general. So let us consider this hypothetical formula where we have force as the LHS, and then you have your RHS as mv square by r square. And I know it's not right, but then you have to prove that it's not right. How do we do that? First, step 1, consider that f is written in terms of its dimensional form. As you see over here, this is the dimensional form, and I'm writing it. Dimensional form for the left hand side, and then forget about left hand side. Go to the right hand side, and then you write the dimensional form of this particular expression, and you get this value. You see that if you consider apples to apples, the left hand side and the right hand side, the exponent of m is the same for both. The exponent of L is different for them, and the exponent of t is the same. So the exponent of L is different, and that's how you say that this equation is not valid, simply based on the assumption that dimensions on both sides should be equal, following the principle of homogeneity, right? So up till now we have talked about utilizing the principle of homogeneity, dimensional forms, etc. But what next? You can use this principle of homogeneity and the dimensional form to develop new relations, and this is something which you might use later in your life, because if you know how a physical quantity depends, and I repeat, how a physical quantity depends on other physical quantities or even fundamental quantities that you have, then you can establish a relation between your unknown quantity and your given quantity within some constraints. The first constraint is it should depend, and the dependency should be of a product power type, right? So you have t is equal to k m to the power x. Let's say if I'm considering the time period of a pendulum, and someone has told you that time depends on mass, time depends on length, time depends on g. How do you validate this? Right, this is very important. So this step is the validation step, and you need to figure out whether it works. Right, so this is the validation step. You establish this relation, and then you figure out whether this can have a particular form or not. Right, so left hand side is time, and I write time in the dimensional form, and then I write m and l, and then g, and then raised to the power of x, y, and z as their corresponding exponents. Right, I write t as in this form, and then I write in this form. As you can see, the advantage over here is the exponent of m is x, and x is equal to 0. The exponent of l is y plus z, and the exponent, and because they are fundamental quantities, they are independent of each other. So they are fundamental quantities. They are independent of each other. So essentially what we have is, let's say I compare x on both sides, and x is equal to 0, y plus z is equal to 0, and then minus 2z is equal to 1, so z is equal to minus half. So that way you establish the relation, and then finally you have the time period, and that is equal to this expression that you have. You see that it does not depend on m, but that came about as a consequence of the calculation that you did so far. Right, so now I'll let you think for a while, and this is the time to breathe, as I say, and think for a while what you have done. Think how you have utilized the relation, how you have utilized fundamental quantities, the principle of homogeneity, and the way the left hand side and the RHS, they are equated to one another to figure out new relations. Right. However, given the number of things that you can do with units and dimensions, and also given that this form as a cornerstone of our understanding of a lot of things, it does have certain limitations, and one of them being that if the dimensions are given, the physical quantity may not be unique, as many physical quantities have same dimensions. So that was the first point that I started with, that if you have two quantities which have same dimensions, just seeing at the dimensional form, it is impossible to figure out what dimension I'm talking about, what physical quantity I'm talking about, I'm sorry. You need to have other data to figure out what exactly we are talking. You must look at the problem, you must analyze the statement, only then you can figure out what we are talking about, right? The values of the numerical constants cannot be deduced from the dimensions. So a few minutes ago I talked about the gravitational constant and how the dimensional form can be established from using this analysis, but then the value of the gravitational constant cannot be established from simply from the dimensional thing that we did. So we can definitely establish a dimensional form, but we cannot establish the numerical value of this. So this is one constraint that we have, also one limitation. Again, the method of dimension cannot be used to derive relation, and that's a third point, other than the product of the power function. To simplify it, it means that if we have a physical quantity that depends on other physical quantities and the relation is power or product, either a power or a product or a combination of both, then it shall work. Other than that, if we have addition and subtraction, we cannot establish a dimensional form we cannot establish a relation between the unknown quantities. Of course, a dimensional form is established once you know the relation between the quantities. So given this equation, we have the time period for a pendulum as this one, but the distance time acceleration equation we cannot. We need integration to solve this, and other methods, like you can do triangle, you can do geometry and a lot of things, but you certainly cannot do it simply based on a dimensional form, right? The fourth point is, and I would ask you to think about it when you read the chapter and understand how the principle of homogeneity works, is the method of dimension cannot be applied to derive formula. If a particular physical quantity depends on more than 3 physical quantities, right? So we are saying over here that the fundamental quantities are 3, and a particular physical quantity depends on more than 3 physical quantities. In that case, the problem would be that there will be more number of unknowns in the equation than the number of equations itself, because we don't have that many fundamental quantities to start with. However, if my explanation is not convincing, I would encourage you to do it by yourself. Take any four physical quantities and try it out, and see that if you can find out the values of the exponents, and convince yourself that it's only 3 or less than 3 physical quantities that you need or you can to establish a relation using dimensional analysis only. For more than 3, you need other data, you need experiments or other forms of computation, and only then you can find out the particular value. The final point for the day is if a physical quantity depends on 3 physical quantities, out of which 2 are same. In that case, again, the relation cannot be established between your unknown physical quantities and a given physical quantity. So dimensional form is possible, but establishing a relation, again, is not possible. So for an example, let's take this case where you have torque, work, and momentum as the 3 unknown physical quantities, as the 3 given physical quantities, and you're asked to figure out what is the relation between them and an unknown physical quantity. So for this case, you see that the dimension of torque and work are the same. So when you're finally getting the result, it would be difficult to assign values to either work or torque. Once again, I'll encourage you to work this out, because this is something which is a bit intuitive. And if you solve the equation, the linear system of equation, and it is very simple, you'll see that you will have a problem in assigning the exponents to these known physical quantities. So that's the end of the discussion for units and dimensions. I will come up with error analysis and other forms of measurement in the next lecture. So until next time.